Okay, so we had been discussing transients in electrical circuit, and what we mainly saw was two different circuits. One was RL circuit. So in the transients, we discussed first RL circuit, and when you have an RL circuit with a voltage source, we called actually this L by R. If I may call this as L and this as R, and this is the VDC. L by R we called as the time constant, and we said that VDC divided by R will be the steady state current or the final current what the circuit achieves once time t is infinity. And if I write the response basically as I of t, what is the kind of I of t I'm going to get during the transient interval? That is going to be ISS multiplied by 1 minus e power minus t by tau. Assuming that my initial condition is 0, that is I'm not going to have any current established already in the inductance. So assuming initial condition, initial current in L is 0. I'm not really establishing any current in the circuit. Okay. And in steady state, inductance will act like a short circuit. It is going to work like a short circuit in a DC excited electrical system. So I'm not having any AC, I'm having only DC. Yes.
Ma'am, VDC by R is equal to ISS when time is equal to infinity, right?
VDC by R equal to ISS when the time is infinity. That is when you are going to reach steady state finally.
Yes.
Yeah. Yeah. So here also, if you try to substitute this e power minus infinity, this becomes 0. That is when it reaches steady state. So the time equal to infinity, what we mean is compared to the time constant. If it is only 10 millisecond, 20 millisecond, then a time of even 10 to 15 seconds is as good as extremely large time. Okay. So if I try to plot this, I'm going to see that if I try to plot with respect to time, how the current is going to start from 0 and then it is going to rise and then it is going to reach a steady state. So if I try to look at the steady state value, right, this is going to be ISS. Okay, so this is the variation of I of t with respect to time. And this is where we said that by the time it reaches 63% of ISS, whatever is the time, that is what is, if I say this is the 63% of ISS value, 0.632 times ISS, this is the time constant tau. That's what we said, right? When we were deriving the expression earlier. And if I try to look at the voltage across the inductance will be full entire VDC when I start with. Because the current is 0, there will not be any drop across the resistance. The entire VDC will come across inductance. So if I try to plot again voltage versus time, the voltage is VL. I'm plotting VL versus time. So if I try to plot VL of t, I am going to have this starting from VDC. And it is going to fall exponentially. So it should have reached 0 at time t equal to infinity. There may be very, very minuscule voltage before that. So this is the way VL of t is going to follow such a trajectory. Okay, fine. The same way we looked at RC circuit also. So in the case of RC circuit, we said that we are going to again have a voltage and we have R, and we have capacitance. And we are assuming that the initial voltage across the capacitance is 0. So this capacitance, initial voltage. So I'm going to assume that Vc of 0 is 0. That is initial voltage across the capacitor is 0. Okay. Now this is VDC. So I'm going to have, this is 0. So between these two, whatever is the voltage difference, that divided by R is going to be the initial current. So I'm going to have a current which is starting from, so I initial is going to be VDC divided by R. Okay. And from there, it is going to decay because I'm going to have slowly the voltage across the capacitance. This VC is increasing slowly. I'm going to have VC increasing exponentially. So I'm going to have VC starting from 0 and it is going to increase exponentially. And final voltage across the capacitance is going to be VDC itself, because the moment it charges to full voltage, there is no potential difference between this point and this point. So the current will automatically become 0. So if I try to plot what is the kind of current I'm going to have. So I of t is VDC divided by R multiplied by e power minus t by tau, where tau is equal to RC. This is the time constant of the circuit for an RC circuit. So it is going to start from VDC by R and it is going to fall, exponentially. So this is going to be the response of I of t. Whereas if I try to plot what is Vc of t, Vc of t is going to be starting from 0 and then it is going to increase exponentially, ultimately to reach the final value which corresponds to VDC. So this is going to be Vc of t. The final value it reaches is VDC. Okay. So please look at how we got the response of inductance voltage versus how we got the current response in capacitance circuit. The two are exactly similar. The same way how we got the current in an inductive circuit versus how we got a voltage across the capacitance in an RC circuit, and both of them look exactly similar. These two look exactly similar. So I just wanted to kind of refresh whatever we had done in the last class. Now with this thing in mind, let us try to do the problem. So this is the first problem in tutorial sheet 3. A 4 microfarad capacitor with an initial voltage of 2 volts is connected to a 12 volts battery through a 5 kilo ohm resistance at time t equal to 0. Determine the current and voltage across the capacitor as a function of time. So let us try to first of all look at what this circuit is. So let me start with this problem. So the first problem says there is a 12 volts voltage source and there is a 5 kilo ohm resistance and there is a capacitance which is 4 microfarad value and it is having an initial voltage of 2 volts. So this is Vc of 0. Okay. And what is being asked is what is Vc of t and I of t after t equal to 0. After, that is when t is greater than 0. So basically you are being asked to derive this when t is greater than 0. Imagine that maybe there is a switch here. So I should show as though there is a switch here and I have this 5 kilo ohm resistance here. This is being closed at t equal to 0. That is what is being given. Okay. So how do we go about doing this? So first thing we have to do is to write Kirchhoff's equation. So let us say this is I. So I should be able to write this as 12 volts equal to 5 kilo ohm Ri plus 1 by C integral I dt. Right? Along with this, I should also include the first initial condition what the capacitance has. So that the initial condition what the capacitance has is 2 volts. So I should say Vc of 0 is also included. That is also opposing this voltage. I hope you understand. This is plus and minus, whereas this is plus and minus, and the current is flowing into the positive terminal of the capacitance. That means the capacitance is going to oppose the flow of current. This is what it is. So I should be able to say 10 volts equal to Ri plus 1 by C integral I dt. Okay, that is the initial condition. So if I try to divide this or differentiate this, let me differentiate this. So differentiating this equation, I should be able to write this as R multiplied by di by dt. This R, in fact, I can bring it along with C. So I can write this as di by dt plus 1 by RC multiplied by I equal to 0. Because 10 volts, when I try to differentiate, it is going to be 0. So from which I think we had already written the solution for this. If you may recall, I'm going to write it once again. So, yeah. Yes.
How did you get the equation 10 volt is equal to Ri plus 1 by C?
What is Vc of 0?
2,
That was 2
okay.
volts. So you have to
Okay.
just minus that, right? Yeah.
Ma'am,
So
why did we write Vc of 0? Isn't 1 by C integral I dt V voltage of capacitor?
1 by C multiplied by integral I dt is the voltage of the capacitor. But when you do the integration, you will always have a constant. And that constant
Yes.
is actually determined by the initial condition, right?
Yes,
Right?
yes.
Yeah. So the initial condition is here 2 volts. Okay?
Okay.
Yeah.
Yeah.
So this is going to be I of t equal to whatever is my initial. So please recall what we did as the derivation in the class. I am not asking you to memorize it, but you should know how we did it. And the general expression for the current in an RC circuit, what we wrote here, right? We did write that VDC by R multiplied by e power minus t by tau. That's what we said. So the same thing we have to write here also, which is going to be VDC or whatever is the initial current, which I have to determine definitely I initial multiplied by e power minus t by tau, where tau is RC. And what is RC here? 5000 multiplied by 4 microfarad. 4 multiplied by 10 power minus 6. How much is it? 20 multiplied by 10 power minus 3 seconds. Please remember tau has the dimension of time itself. So this is 20 milliseconds. Okay. So 1 by tau is going to be 1 by 20 into 10 power minus 3, which happens to be 50. This is going to be 50. Okay. So 1 by second is, so you can say 50 second power minus 1 if you want to. Doesn't matter. It is essentially hertz. Cycles per second. Cycles is generally doesn't have a dimension. So generally you are going to say this is second power minus 1. That's fine. So what is I initial now? I want you to tell me what is I initial. Anybody? How much is the initial current? Yes, please give it a try. How much is the initial current? Yeah.
VDC by R.
Yeah, VDC by R. How much is VDC? That is my question here. Is it 12 or 10?
Ma'am, 10.
10. Why is it 10? Good. Why is it 10?
Ma'am, because 2 volt is opposing the initial voltage.
Exactly. Exactly. Very good. So this is going to be 12 minus 2 divided by 5 kilo. Right? Okay. So that is 10 volts divided by 5 kilo ohm, which gives me 2 milliampere. Right? So I'm going to have I of t equal to 2 multiplied by e power 1 by tau is 50 we said. So e power minus 50 t milliampere. Please remember you have to write the units. Otherwise it doesn't make any sense. 2 milliampere is the initial current. So from 2 milliampere it will keep on decaying. You get my point? So this is going to be I of t. Is this clear? Is it okay?
Ma'am, why did we differentiate, like differentiating di by dt plus I by RC? I didn't get it.
If you want to solve the differential equation, I am converting an integral equation into differential equation. That's all. This was an integral equation. Rather than that, I am just trying to do it as a differential equation. That's all. You could have written the whole thing in terms of voltage also. You can write C dV by dt plus V by R. That is also fine. What is this? This becomes the KCL equation. C dV by dt is IC, V by R is IR. You can do that also. But I wanted to just write the mesh equation. That is also fine. Okay. So I have written the mesh equation. You can do it the other way around also. Okay. So now let us try to get, this is the I expression. Now I want to get what is Vc of t. So Vc of t is 1 by c integral I dt. With the initial condition being with Vc of 0 being 2 volts. This is already given. So I have to use this expression basically to calculate. Now I can write this as 1 by C multiplied by, I can say 2 e power minus 50t dt. I have to do this plus some constant. Right? Whenever you do the integration, you are going to have some constant. So I'm going to write this as 1, this is milliampere. So I have to write this as 10 power minus 3 multiplied by this. Please remember this. I cannot ignore that 10 power minus 3. So I should say 10 power minus 3 divided by 4 into 10 power minus 6. Let me get this 2 also out. 2 into 10 power minus 3. And I have to integrate this. What is the integration for this? E power minus 50t divided by minus 50. Right? Plus C1. Right? So now I'm going to have 2 and 4 I can cancel. This is 2 and 2 multiplied by 50 is 100. So I can say minus 100 and on the top I'm going to have this is 10 power minus 3 left over here. So this will be 1000. So 1000 divided by 100 into e power minus 50t plus some constant of integration C1. So I should say again 10 e power minus 10 e power minus 50t plus C1. How do I solve for C1? That is by using the initial condition. So this is Vc of t. At t equal to 0, the voltage across the capacitor is 2 volts. So what is C1? That's what I have to calculate. So this is 2 equal to, which is Vc of 0, VC of 0 is 2, which is equal to minus 10 multiplied by e power minus 50t. E power minus 50t is how much? 1. E power 0 is 1. So I'm going to have minus 10 plus C1. So C1 is going to be 12 volts. Correct? So C1 is going to be 12 volts. So I should be able to write this as VC of t equal to 12 minus 10 e power minus 50t volts. Okay, so let us try to look at problem number 2. So let me try to take out problem number 2. So problem number 2 says find IV I1 in figure 1 if the source is of 9 volts magnitude. So this is 12 ohm, 6 ohm and 5 millihenry. Okay, so let me try to redraw the circuit here. So I'm having a 9 volt source. There is one resistance here, which is 12 ohm. And I have another resistance here, 6 ohm. Okay. And I'm going to have 5 millihenry as the inductance here, which is coming across A and B. Okay. So let me go back here and draw this 5 millihenry here. Okay. Now, these two terminals are given. This is A and this is B. Because there are two resistances given, if I can convert this portion completely into the equivalent Thevenins, then I would be able to deal with this as one particular R and one L along with the voltage source. So it may be worthwhile to find Thevenin's equivalent as seen from A, B. Okay. So if I try to look at it as Thevenin's equivalent from AB, first of all, open circuiting AB. Let me try to look at what is the kind of voltage I have. It is essentially 9 volts along with 12 ohm and 6 ohm. So the current is going to be 9 by 18, which is 0.5 ampere. What I get is a 0.5 ampere current. So VAB is going to be voltage across the 6 ohm resistance. So I'm going to have 3 volts as V Thevenins. Is that clear? Okay. So I'm going to have V Thevenins as 3 volts. And when I want to check what is RTH, I can simply do one thing, that I can simply connect it like this. In fact, I have to short circuit the voltage source, right? If I want to really look at RTH, that is also one way. If there are no dependent sources, I can simply have 12 volts here, 12 ohms here and 6 ohms here. And I want to know what is the equivalent resistance across this. This is going to be RTH. So RTH is 12 multiplied by 6 divided by 12 plus 6. Right? So that is going to be 4 ohms. So my RTH in this particular case is going to be 4 ohm. So I can write the entire circuit in a simplified manner, somewhat like this. So I'm going to have a 3 volt source, which is V Thevenin, and I'm going to have a 4 ohm resistance, and I'm going to have a 5 millihenry inductance. So I can definitely calculate what is tau. So tau is going to be L by R, which is going to be the time constant. So I'm going to have this as 5 millihenry divided by 4 ohm. So which is going to be 1.25 millisecond. Right? This is going to be the tau value. Is that clear? Okay. Yeah.
Ma'am, here I didn't get, how did you get 3 volts VThevenin? Like, isn't it in parallel? Shouldn't the inductance matter? We are ignoring it.
When you calculate VThevenin across AB, would you not open circuit this terminal? You are supposed to see the open circuit voltage, right? VThevenin is basically the open circuit voltage across the terminals in which you are calculating the Thevenin circuit, equivalent circuit. So it is VThevenin is the open circuit voltage and ISC is the short circuit current. If I try to short circuit this terminal, so if I want to calculate the Norton equivalent, I should have short circuited. So I should have done this and I should have short circuited this. And what I calculate as the short circuit current is the Norton current. Right? This is what we talked about when we talked about Thevenin's theorem and Norton's theorem. Whichever terminal is mattering to us, that particular terminals we have to either open circuit if I want to calculate the VThevenin value, and I have to short circuit this if I want to calculate the Norton current. Right? Okay?
Yeah, ma'am, got it.
Yeah. So that is the reason why we are getting this as 3 volts, right? If I didn't want to calculate R Thevenin's this way, I could have calculated the short circuit current. How will I calculate the short circuit current? This is 9 volts. This is 12 ohm. This is 6 ohm. But because the short circuit is existing in parallel with 6 ohm, this has to be ignored completely. So I'm going to have 9 divided by 12. That is going to be the short circuit current. Right? How much is it? 9 divided by 12 is 3 by 4, 0.75. So I have to have VThevenin divided by ISC. So 3 divided by 3 by 4, which is going to be 4 ohms, which we have got anyway here. Okay, so you can calculate the Thevenin's resistance either way. You calculate the short circuit current and VThevenin's divided by short circuit current will give you the resistance, Thevenin's resistance. Okay, fine. So this is going to be the time constant of this circuit. Now what are they asking us to solve? They are asking us to solve, find I is the current through the inductance, V is the voltage across the inductance, and I1 is the current through the 12 ohm resistance. Okay, so let us try to look at this. Where is that? Okay, so first of all, let us try to calculate what is the I of t. How do you calculate I of t? I of t will be ISS into 1 minus e power minus t by tau. Right? What is ISS in this case? ISS is going to be 3 divided by 4. So 0.75 ampere. Right? This will be 3 by 4 multiplied by 1 minus e power minus t by tau. So it is going to be minus t multiplied by 1000 divided by 1.25. Because it is 1.25 millisecond, I am writing it like this. So this is essentially 0.75 multiplied by 1 minus e power minus 800 t. 1000 by 1.25 is 800. So that is going to be minus 800 t. Okay. So that is essentially going to be the current expression for this circuit. Current through the inductance. If I try to plot, this is the way it is going to be. And what is the voltage across the inductance? L di by dt. isn't it? Just like how we say current through the capacitance is C dV by dt, right? The same way voltage across the inductance is L di by dt. And what is L? 5 multiplied by 10 power minus 3 multiplied by di by dt. I have to say 0.75, anyway it will be outside, and d of 1 minus e power minus 800t divided by dt. Okay, so how do we do that? 5 multiplied by 10 power minus 3 multiplied by 0.75 divided by, so I'm going to have a negative sign and minus 800 also, right? Multiplied by e power minus 800t. That's about it. Okay, is that fine? So how much is this? Is the minus 800 here? Have I hope, yeah. So this is actually, this is 10 power 2 and how much is this? How much is this coming to? Can you tell me? This is 5 into 10 power minus 3 is millihenry. Yeah. So how much is this? Can you calculate this and tell me how much this is?
Ma'am, here in the instantaneous voltage, we can also use VDC e power minus t by tau, right?
What is it?
VDC into e power minus t by tau for voltage of an inductor in
You
RL
can.
circuit.
You can. You are saying that basically VDC into e power minus t by tau. That also you can use. In this particular case, sorry, this minus 800 cannot come down. No, it should be plus 800. It is not integration. It is differentiation. You guys are sleeping or what? Because nobody is telling me that if this 800 has to come in the numerator, not in the denominator, right? Yes or no? So what you say is true. Now this will come out to be 3. I think this is coming out to be 3. This is 5 multiplied by 3 by 4 multiplied by 800 into 1 by 1000. So this will come out to be 3. 3 into e power minus 800t, which is coming out to be this. Right? Whoever asked me this question, VDC multiplied by e power minus t by tau, that's what we are getting. So this is the voltage. So you can do it from the first principle, or if you want to remember this expression and you do it, that's also fine. But if there had been an initial established current in the inductor, then you could have some difficulty. That you have to be careful. Okay? If you use directly the formula, huh? Yeah?
So direct formula, what is the disadvantage? I didn't get it.
If you try to have the direct formula simply applied, and if it had been some initial condition or something given, which you have not taken into consideration, then it could be a problem. Especially when you are doing integration, you know, if you kind of ignore some initial condition or final condition or something that is given, then your answer will definitely not match. Your response will be not the correct one. That's what I'm trying to say. So you should be careful, especially if some initial conditions are given. Okay. Now, the other one what they have asked is the current through this particular resistance. They have also asked for what is the current through this particular resistance. See, one thing we can say is this voltage is same as VL. Isn't it? Steady state current you can always calculate. That is not a problem. We are not talking about that. This is going to be basically VL. This voltage is same as VL. This and this are in parallel. These two are in parallel. This 6 ohm and 5 millihenry, both of them are in parallel. So this is VL. So 9 minus VL of T divided by 12 will give me directly I. So I can say I through 12 ohm resistance is going to be 9 volts minus VL of T divided by 12 ohm itself. So I can write this as 9 minus 3 e power minus 800 times t divided by 12. That's it. Is that clear? Any questions on this? Any questions on this? Okay. So let's try to look at the next problem. So let me just open this. Yeah. So the next problem is initial voltage across capacitor in figure 2 is 17 volts. Okay, this is 17 volts. And at time t equal to 0, the switch is closed. Determine VA, VB, VC, IAB, that is the current from A to B, and current from B to C, and IAC. IAC is current from A to C. That is through 6 kilo ohm resistance. Okay, all three are being asked, and the three voltages are also being asked. Okay, so let me first of all draw the circuit and see how we can proceed. So there is no other DC source connected, only this 9 microfarad capacitor is connected, and it is having an initial voltage of how much? What was given in the problem? 17 volts. That was 17 volts. So VC of 0 is 17 volts. I'm assuming plus here and minus here. And if I look at rest of the circuit, I'm going to have a 2 kilo ohm here. And this is going to be B. And this is going to be 4 kilo ohm. And this is C. And this is 6 kilo ohm. And this point is A. And this is 3 kilo ohm. And this is 12 kilo ohm. And these are all connected together. This is the common ground. Okay. So there are three nodes specifically A, B, and C. So if we are writing the nodal equation corresponding to A, B, and C, let's say, let me write node equations. Okay. So the equation at node A. So at node A, I should say whatever is the voltage at node A, VA, divided by 3K. Because if I assume this is the ground, so this is going to be 3K. And I'm going to have VA minus VB divided by 2K. And I'm going to have again VA minus VC divided by 6K equal to 0. Right? This is going to be the first equation. And second equation I can write for, we will simply,
4K.
yeah. Yeah.
Okay, at no, okay, no number.
We are only talking about node A, nothing else. Okay. So we are talking now about node B. So if I try to write at node B, right? How should I write the node B equation? Tell me. If this current, we need to solve for the capacitance current. Let me look at the circuit diagram once again. I need to solve for this current I through the capacitor. So let me write that once again here. This is current I. What they have shown as current I is this. So I can write at node B, one current is I. Okay. So I is going to be equal to VB minus VA divided by 2K, right? Plus VB minus VC divided by 4K. I have to solve for this current I, which is the transient current through the capacitor. So I have taken that as this particular variable. Okay, fine. What is the next one? At C, let us write. At node C, what is the equation? Tell me. What is the equation at node C?
VC minus VB by 4K.
Great. Yes.
VC
Plus.
minus, plus VC minus VA by 6K.
Yes. Plus.
VC minus VA by 3K.
No.
Can we write that?
No.
Sorry, by 12K.
This is ground.
12K.
This is ground. This is ground. So VC by 12K. This is ground. This is my reference node. Equal to 0. Okay. Fine. So now let us try to simplify this and see whether we are able to get any expression. Okay. So because it is all K, the currents that we are going to get are in milliampere. Please understand. So I'm going to remove K completely. I'm going to say VA by 2, VA by 3. So let me take a common denominator. Why not? Okay, I can make the common denominator to be 6 here. Okay, so if I take the common denominator to be 6, I'll get here 2 VA and this is going to be 3 VA, 2 plus 3, 5, 5 plus 1, 6. So I will have 6 VA. Okay, and then again, let me take a common denominator. We had taken a 6, right? So VB, if I try to see, this is 3 VB and there is no other VB. So this is 3 VB. Okay, and then VC I have only 1. So minus VC equal to 0. Okay, fine. This is equation number 1. So this is at node A. Then node B, let me try to again take the common denominator. If I try to do 4K as the common denominator. So this is VB, 2 VB, and this is one more VB. So I'm going to get 3 VB. So I'm going to get 3 VB plus, and here I'm going to get 2 VA. So this is minus 2 VA. Okay. And VC I'm going to get as it is. Equal to I milliampere. Let me write this is all in milliampere. So this is going to be equation number 2. Can we write for equation number 3? So here can I take 12 as the common denominator? Let me take 12. So this is 3 VC. This is 2
in
VC.
Equation 2, the denominator will go and get multiplied with 4, right? So it will be 4i, right?
4i. You are right. Thank you. Yes, I made a mistake there. 4i milliampere. That's right. Okay. Now we are going to have the other one. This one is 3 VC plus 2 VC, 5 VC and 6 VC. So I'm going to have 6 VC. Okay, plus 6 VC. Anything else? VB has to be, this has to be multiplied by 3. So 3 VB, fine. That is the only thing. So this is going to be minus 3 VB. Right. And then anything else? VC, we have already done. VA is 2 VA. So minus 2 VA. Equal to 0. This is equation number 3. I want you to manipulate this. And when you manipulate this, finally we are getting VB equal to, please verify this. I want you to really verify this. VB equal to 34 by 9 I milliampere. I want you to just solve this completely using these three equations. If I simplify this, we are getting VB equal to 34 by 9 I milliampere. So if we are looking at this, the current that is flowing here, I, that is supposed to be equal to 34 by 9 times I milliampere. Okay. This particular capacitance is 9 microfarad capacitance, and it is having a voltage which is corresponding to VB. VB is same as V of C. I hope you understand. The node voltage, whatever is VB, that is same as the capacitance voltage itself. Okay. So if I am going to have a current which is 34 by 9 milliampere, which is actually the current that is flowing through this, then will we be able to arrive at the equivalent resistance seen by this portion along with the capacitance, and whether we will be able to arrive at the RC time constant. That is what we are going to look at. How do we arrive at the equivalent resistance seen by this particular branch, and then whether we will be able to draw this as just a RC circuit, R and C, whether we would be able to draw it like this, and if we have the initial VC of 0, and if we are able to get the R equivalent corresponding to this, whether we would be able to arrive at finally the equivalent time constant and everything, and then we will be able to solve further.